See, say you throw a stone, okay, vertically you throw a stone. Now it will go to a certain height and it will fall back down, correct? Now, same thing, let's say you have a cannon. Let's say you hit a cannonball using a cannon. That also it will go to a certain height and then it will fall back, correct? Now, say you have incredible strong shooter and then the shooting some machine is there. So, say you throw something using that machine. Now, there also it might go to a certain height and it can fall back. Now, if you have enough strength, you can throw something out of Earth's atmosphere, correct? Now, how much of energy is needed? And what should be the velocity? That velocity and that energy is what we call as escape velocity and escape energy. Okay, so escape velocity is the minimum velocity given to the body so that it can escape Earth's gravitational pull. So that is what we call as escape velocity. Okay, and escape energy is the kinetic energy the body possesses so that it can escape the Earth's gravitational pull. That is escape energy. Now, this escape velocity and escape energy plays a very important part because all the satellites and all the rockets, whatever they launch, so everything they need to consider this escape energy and escape velocity because they have to place the satellite in an orbit, correct? So that which is basically some around hundreds of kilometers above Earth's surface. So when we talk about escape velocity, now how much of velocity Earth has, this escape velocity? Now we'll try to derive an expression for the escape velocity. Okay. So what we have, suppose let's say a body of mass m. So this is placed on Earth. Let's say the mass of the Earth is me and radius of Earth is re. See here, if I'm throwing the object or the body at an escape velocity of VE, then what we have the potential energy at the surface, say U1 is equal to minus GME into M divided by RE, the gravitational potential energy, and the kinetic energy or the escape energy will be half mVE square, correct? See, say we have an object and that object is going to infinity. That means it's going out of Earth's gravitational pull. See, if that is the case, then my distance will become very, very, very big. That means the gravitational potential energy becomes zero, correct? So, at infinity, we have U2 is equal to minus GME into M divided by infinity, which becomes zero. Correct? So, my U2 value, that means at infinity it is 0. So, if it's going to infinity, once it goes to infinity, my potential, the kinetic energy will also become 0. Okay, the kinetic energy, what we say. So, what we have U1 and K1, that is on the surface of the Earth. So, and U2 and K2 at infinity, some point. Now, by principle of conservation of energy, we have energy can either be created nor be destroyed. So, the initial energy and final energy should be the same, correct? Now, we'll use this concept and try to figure out what is the escape velocity. We have K1 plus U1 is equal to K2 plus U2. So, we have half mVE square minus GME into M divided by RE is equal to 0 plus 0. Now, we transpose the potential energy to RHS. So, we have half mVE square is equal to GME into M divided by RE. Now, M and M gets cancelled. So, we have VE square is equal to 2GME divided by RE, or VE is equal to root of 2GME divided by RE. Okay, now we got this as the expression for the escape velocity. Now, if you carefully look at the formula, is the escape velocity dependent on mass of the body? No, it depends on the mass of the object, mass of the Earth, and radius of the Earth, and gravitational constant. Now, if you look at it, mass of Earth, radius of Earth, and gravitational constant, all three are always constant. So VE is a constant. That is, the escape velocity is always a constant. Now, if you apply all the values, because ME, RE and G are known. So once we apply this, we get a particular value, that is 11.2 kilometer per second. That is, if you throw an object at a speed of 11.2 kilometer per second, then that object can escape Earth's gravitational pull. Alright, so this is the formula for escape velocity. Now, we can also write escape velocity in terms of the acceleration due to gravity. Let's see how that goes. We have G is equal to Gme divided by Re square. So Gme is equal to Re square into G. So substitute that here. See, if you substitute that here, we get Ve is equal to root of 2 Re square G divided by Re. Re gets cancelled. So we have root of 2 Re into G. Right? So we have the radius of Earth and acceleration due to gravity. Again, these two are constants. Now, even here also, if you apply the value of radius of Earth is 6,400 kilometers, like approximated value. And the value of G is 9.8 meter per second square. Correct? So if you apply that, again we'll get 11.2 kilometer per second. So remember, escape velocity doesn't depend on mass of the body. It depends on how big the planet is. That is, bigger the planet, so more will be the mass. So more the mass, more is the escape velocity. Understood? So see, for Earth, which is about 6,400 kilometers in radius, it has an escape velocity of 11.2 kilometer per second. Moon has around 1,600 kilometers. That's the radius of Moon. If you apply that, you will get around 2.38 kilometer per second. So that is the escape velocity on Moon's surface. Like if you throw an object at a speed of 2.38 kilometer per second, that will escape Moon's gravitational field. Fine. So as the body becomes bigger and bigger, see, radius will keep on increasing. So as radius increases, the escape velocity will also increase. Fine. So this is the escape velocity. So escape velocity is Ve is equal to root of 2 Re into G, or Ve is equal to root of 2 Gme divided by R.